AP Chemistry Unit 1 covers atomic structures and properties. Even though it might be considered the easiest unit, it lays an important foundation for everything else you'll learn in this course. Hi there, my name is Jeremy Krug, and you've found the place for all things AP Chemistry. You're about to learn the 10 most important things you've got to know from Unit 1. If you're new here, welcome to my channel. Take a look around, check out my AP Chemistry playlists, that's where the action is, and make sure you subscribe because I don't want you to miss a thing this year as you're learning chemistry. If you learned something from this video, remember that one of the greatest compliments you can give me is to tell your friends about my channel. And if you're serious about getting that 5 on the AP exam in May, check out my ultimate review packet for AP Chemistry. It's got the full review videos for every unit, complete study guides, practice questions, my exclusive tips and tricks for each unit, and 2 full practice exams in the AP Exam Simulator. And as a special gift to you, everything for Unit 1 is part of an absolutely free trial that you can get over at ultimatereviewpacket.com. Now, here are the 10 things you've got to know from Unit 1. Number 1. The mole is a unit that refers to a specific quantity of fundamental particles for a substance. For any substance, 1 mole contains 6.022 times 10 to the 23rd fundamental particles. So, if we're asked how many molecules are found in a 0.732 mole sample of H2SO4, we use dimensional analysis. We start by writing down what's given to us, 0.732 moles of H2SO4, and we're trying to convert to molecules. So in our conversion factor, we put moles on the bottom and molecules on the top, since that's what we're converting to. And we know that 1 mole is equal to 6.022 times 10 to the 23rd molecules. So we cancel moles, and on our calculator we take 0.732 times Avogadro's number, and the answer is 4.41 times 10 to the 23rd molecules. What if we were asked how many oxygen atoms are found in this same sample? Well, we've just determined how many molecules of H2SO4 we have. If we're converting to atoms of oxygen, in our conversion factor, molecules of H2SO4 go on the bottom, and atoms of oxygen go on the top. And this subscript of 4 right here tells us that there are 4 atoms of oxygen in every 1 molecule of H2SO4. So we can cancel molecules of H2SO4, top and bottom, and multiply. And we find that the sample has 1.76 times 10 to the 24th atoms of oxygen. Number 2. In the laboratory, we more commonly measure substances in terms of mass. 1 mole of any substance is equal to the total of the atomic masses of the atoms found in that substance expressed in grams. So if we're asked what is the mass of 0.400 moles of ZnCl2, zinc chloride, we can start by writing down what's given to us. Since mass is measured in grams, in our conversion factor we put moles on the bottom and grams on the top. To determine how many grams are in a mole, we have to consult the periodic table for these elements. For a compound, we always add the total atomic masses of the elements. We have 1 zinc atom at 65.38 grams, and then we have 2 chlorine atoms at 35.45 grams apiece. When we add these together, we find that the mass of 1 mole of this substance is 136.28 grams. So we put that into our conversion factor. And of course, that's equal to 1 mole. We cancel moles, multiply, and find that the mass is about 54.5 grams of zinc chloride. Number 3. The mass spectrum graph for a pure element represents all the isotopes found in that element. The height of each peak represents its percentage abundance, while the mass and abundance of each isotope can be used to estimate the average atomic mass of the element. When you see a mass spectrometer graph like this, we see it has 2 peaks. That means this element has 2 isotopes, and the height of the peak represents how abundant each of those isotopes is. And since the peak with a mass of 107 is a little bit taller than the other one, that means that the isotope with a mass of 107 AMU is more abundant than the one with a mass of 109 AMU. We can see the actual percentages by looking at the y-axis. The 107 isotope is 53% abundant, while the 109 isotope is 47%. We can use this information to estimate the average atomic mass of the element. We take the isotope's masses and multiply them by the decimal equivalent of the percentage. So we take 107 and multiply it by 0.53. We do the same thing for the other isotope, 109 times 0.47. When we add those two products together, we find that the average atomic mass of this element is pretty close to 107.94. Now, we can match that up to the periodic table and see that this is silver. So we could get a pretty good estimate of the average atomic mass of an element just by looking at the mass spectrum given for an element. Number 4. A chemical formula can be used to calculate the molar mass of a compound. That data can be used to determine the elemental composition for that compound. Likewise, percentage composition can be used to calculate a compound's empirical formula. If we're given the compound C6H12O6 and we're asked to determine the percentage composition, we take each subscript and multiply it by the respective atomic mass for that element. Then we add those together to find that the total molecular mass of the substance is about 180.16 AMU. We take the individual product from each element and we divide it by that total molecular mass. So in the case of carbon, 72.06 divided by the total is 40%. It's about 6.72% hydrogen by mass, and for oxygen it's 53.28% by mass. Now we can go in the opposite direction too. Maybe we're given the percentages and asked to determine the empirical formula. Here, a compound contains 22.55% phosphorus and 77.43% chlorine by mass. What is the empirical formula? Well, we take those two percentages and write those as gram values since these are percentages by mass. We convert each of those to moles. So for phosphorus, we divide by its atomic mass, 30.97, and find that we have 0.7281 moles of phosphorus. We do the same thing for chlorine and divide by its atomic mass and find that we have 2.184 moles. Then we divide by the smallest of those mole values and we find that the smallest whole number ratio of these elements is 1 to 3. So the empirical formula of this compound is PCl3. Number 5. Coulomb's law describes the attraction between two charged particles. When charged particles are closer together, the attraction between them is stronger. Likewise, when the magnitude of charged particles is higher, the attraction is stronger. So if we're comparing two pairs of charged particles, one pair is +1 and -1, and the other pair of charged particles is +2 and -2, we'd say that the +1 and -1 pair will have a weaker attraction to each other because the magnitude of charge is lower. On the other hand, the +2 and -2 charged particles will have a stronger attraction for each other because they have a higher magnitude of charge. Likewise, a +3 and -3 pair of charged particles would have even stronger Coulombic attractions than both of these. We also have to remember that distance plays an important part in Coulomb's law. Looking at these two pairs of charged particles, in the first pair, the two charged particles are farther apart from each other. So these particles will have a weaker attraction for each other. On the other hand, the second pair shows that the particles are closer to each other. That means they'll have a much stronger attraction for each other. Remember, Coulomb's law has two factors, magnitude of charge and distance. The higher the magnitude of charge, the stronger the attraction. And the closer the charged particles are to each other, the stronger the attraction. Number 6. Ground state electron configurations can be written by following a very specific pattern on the periodic table. Electrons are normally added to sublevels in order of increasing energy, as predicted by the Aufbau principle. To write an electron configuration, we need to know a very specific pattern of how they're written. The best way to get better at these is to practice. For example, for the ground state electron configuration of magnesium, we always start at the beginning of the periodic table. We have 1s2, 2s2, 2p6, and then 3s2. You can also write the noble gas abbreviation. We just back up to the previous noble gas, which is neon, and pick up from there, 3s2. If we have one that's a bit longer, like yttrium, we can see where that one's located, and as we always do, we start at the beginning. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 10 boxes in that section, 4p6, 5s2, and 4d1. Or if you prefer, you can back up to the previous noble gas, which is krypton, and pick up from there, 5s2, 4d1. Number 7. Each peak in a photoelectron spectrum diagram represents a sublevel of electrons in an atom. The sublevels are read in order from left to right, in order of placement, while the height of each peak is proportional to the number of electrons in that sublevel. If you can write an electron configuration, you can read a photoelectron spectrum diagram as well. So the first peak is always 1s. The second peak is 2s, and you know that 2p is after that, and then 3s, and then 3p. Now, the height of each peak is proportional to however many electrons are in that sublevel. So for all three of these s peaks, they're the same height. And we know that s sublevels tend to have 2 electrons in them. Now, the 2p peak is 3 times higher than those s peaks. So that means it has 3 times as many electrons, which is 6, 2p, 6. Now, the last peak here, the 3p peak, is twice as high as those s peaks. So that means it has twice as many electrons. So that would be 3p4. And if you know your electron configurations, you can match this up to the periodic table and see that this is sulfur. Remember that on the x-axis, the binding energy gets lower as you go from left to right on this diagram. And that makes sense because the outermost electrons have the greatest energy. And because of that, it actually requires less energy to remove them. That's why binding energy gets smaller as electrons get farther away from the nucleus. Number 8. When comparing atoms in the same period, or row of the periodic table, their differences are best explained by comparing the number of protons they have, which affects the effective nuclear charge of those atoms. Generally speaking, as you move toward the right on the periodic table, atoms have a smaller atomic radius, a higher ionization energy, and a higher electronegativity. And as you move toward the left, atoms generally have a larger atomic radius, a lower ionization energy, and a lower electronegativity. The main reason is their number of protons and nuclear charge. If we're asked to compare the atomic radius of potassium and bromine, we'd say bromine has a smaller atomic radius than potassium. Why is that? Because bromine has more protons to attract its electrons. Remember, more protons means more magnitude of charge, more Coulombic attraction. And since the Coulombic attraction is stronger, the atomic radius of bromine is smaller. What about ionization energy? We could say that bromine has a greater ionization energy than potassium. Why? Because bromine has more protons to attract its electrons. Remember, more protons, greater magnitude of charge, and greater Coulombic attractions. Since the Coulombic attraction is stronger, it's going to require more energy to remove an electron from bromine than from potassium. Number 9. When comparing atoms in the same group, or column of the periodic table, their differences are best explained by comparing the number of electron shells they have, which affects the distance of those atoms' nuclei from their outermost electrons. So as we move toward the top of the table, elements will usually have a smaller atomic radius, a higher ionization energy, and a higher electronegativity. And toward the bottom of the table, it'll be the opposite: a larger atomic radius, a lower ionization energy, and a lower electronegativity. So if we're asked to compare the atomic radii of oxygen and tellurium, we'd say that oxygen has the smaller atomic radius. Why is that? Because oxygen has fewer electron shells than tellurium. Remember, fewer electron shells means the outermost electron shell is closer to the nucleus. So the atomic radius of oxygen is smaller. What if we're asked to compare their ionization energies? We'd say that oxygen has a greater ionization energy than tellurium. That's because oxygen has fewer electron shells than tellurium. Remember, fewer electron shells means the distance is lower, and lower distance means stronger Coulombic attractions. And since the Coulombic attraction is stronger, it requires more energy to remove an electron from oxygen. Number 10. The number of valence electrons in an atom can be predicted by that element's position on the periodic table. Elements in the same column tend to form similar compounds because elements in the same column tend to form ions with the same charge. There's a pattern for valence electrons on the periodic table. In group 1, elements have 1 valence electron. Group 2, they have 2. Group 13, they have 3 valence electrons, all the way up to the noble gases, most of which have 8 valence electrons. And because of this, we can predict the charges of many of the ions for these elements. For example, because of sodium's location on the periodic table, we can predict that the sodium ion will have a charge of +1. Because of oxygen's position on the periodic table, we would expect its ion to have a -2 charge. Now, when sodium and oxygen ions make an ionic compound, we see that 2 sodium ions are needed to counteract the -2 charge from the oxygen ion. So that's why the formula of the ionic compound between these two ions is actually Na2O, which we call sodium oxide. Notice that lithium and potassium also have a +1 charge when they form ions. So that means that lithium oxide and potassium oxide would have these formulas. And those two compounds would be chemically similar to sodium oxide because lithium and potassium are chemically similar to sodium since they're in the same group of the periodic table. And that's it. Those are the 10 most important things you've got to know from Unit 1. If you're serious about upping your game for the AP exam, my Ultimate Exam Slayer for AP Chem has 60 AP-style multiple-choice questions for Unit 1 and for every one of the 9 units. That's way more than AP Classroom. You can get my Exam Slayer along with the Ultimate Review Packet, and you'll have everything you need to succeed this year in AP Chem. Go check it out over at ultimatereviewpacket.com. Thanks so much for watching. Thank you even more for subscribing, and I'll see you soon.